Thank you very much. It's my great pleasure to be invited to give this talk. This is my first and hopefully not last visit to Nottingham. So thank you very much. Let's start today with setting the stage. The basic challenge I'm interested in is to understand all varieties that embed into projective space. And today, mostly for simplicity, we'll work over a field, which I'll assume is algebraically closed. So this is an overly ambitious question in many ways. I can't possibly classify these things in a very strong sense, but this has been a motivating question for algebraic geometers for a long time. Grothendieck recast this question in the 60s in a geometric form. He showed that closed subschemes, that's a terrible view, in projective space are parametrized by another space, which he called the Hilbert scheme. I'll denote it by Hilb Pn to emphasize the ambient space. So in fact, Grothendieck wasn't only interested in projective space, but today I'm going to concentrate exclusively on projective space. To get a sense of what this means, at maybe the simplest level, if we have a projective subvariety, then it corresponds, every projective subvariety corresponds to a point in this space. So somehow just at the level of sets, we have a bijection. But it, of course, being Grothendieck, it had a more functorial interpretation, which I'll say informally can be captured as saying deformations of our space X correspond to nearby points. In the Hilbert scheme. So the topology on this set captures interesting geometric information about the spaces we're classifying. And maybe one further example of this connections, if we have a one parameter family of closed subvarieties or subschemes, that corresponds to a curve in the Hilbert scheme. So this really recasts the question. If you want to understand the subschemes, it turns it into a question, what is the geometry? What can we say about the geometry of this Hilbert scheme? So the basic problem from this point of view is the following. We want to describe the geometry of these spaces, and in fact they turn out to be, this turns out to be a projective scheme itself. This is sort of a common miracle in algebraic geometry, is if you take a collection of objects you want to understand, they can often be classified by another geometric object in the same category, which is really quite nice and amusing. Why did he call it the Hilbert scheme? That isn't clear from what I've said so far, and so let me say a little bit about that. So Hilbert, in a famous paper published in 1890, proves many things. It answers a bunch of questions raised in invariant theory, but from the purposes of this talk, the key thing is he shows there exists a polynomial, now called the Hilbert polynomial, for every subscheme in projective space. So this is a univariate polynomial with rational coefficients. And it really defining property is that when we evaluate this polynomial at large integers, we get the dimension of a vector space, namely the homogeneous coordinate ring, well, a piece of the homogeneous coordinate ring for the subscheme in question. So the quotient of the polynomial ring defined corresponding projective space by the homogeneous ideal or a homogeneous ideal that cuts out your subscheme. And this works for integers large enough. Maybe it's useful. Well, it's morning for me, so warming up with an example would be nice. So the twisted cubic curve is among the most famous first examples of a projective variety. So it's the image of the map from P1 into P3, given explicitly by taking a point in our projective line, so that's a ratio of numbers, and mapping it to the monomials of degree 3 in these two variables. So z0 cubed times, well, z0 squared times z1, and z0 times z1 squared, and finally z1 cubed. So it has a very explicit description, and we can write down the well-known equations that cut this out in these coordinates. We get x1 times x3 minus x2 squared, x0 x3 minus x1 x2, x0 x2, terrible 2 times x1 squared. So this happens to be cut out by 3 quadratic equations, and in fact, using a computer algebra system with this explicit ideal, you can compute the Hilbert polynomial. You can do it by hand in this case, explicitly count monomials. You can also take the fact that you know the Hilbert polynomial for P1 and understand how it behaves under this map. So several different ways in this concrete example, you can compute the Hilbert polynomial, and you find that it's 3t plus 1. So what Grothendieck really proves, well, stronger than what I stated before, is that this classifying or parameter space, get Grothendieck's name up here, decomposes. We have the disjoint union this larger parameter space that classifies all subschemes, breaks up as a disjoint union, and the pieces are indexed by Hilbert polynomials, and the disjoint pieces, well, classify subschemes of our projective space, except they're all the ones that have a given or a fixed Hilbert polynomial. So what we're really interested in this classification problem is to understand these pieces, right? It breaks up. We wanted to understand all of them, and Grotnink's told us it breaks up into understanding the pieces given by a Hilbert polynomial. And it's this decomposition that really gives it the name, the Hilbert scheme. So this is the idea. In fact, Grotnik shows this is true much more generally. It's not just true for projective space, but for projective varieties, projective schemes, and in fact, with some effort, you can even do it for projective stacks. And well, I'm not going to go that way. We're going to concentrate on projective space today. So we're not the first to think about this. And in fact, there are some well-known results and nice things to say about the geometry of Hilbert schemes. The first, amusingly, predates the existence of Hilbert schemes. So this is, of course, not the way Macaulay said it, because he didn't have the language of Hilbert schemes, but he was analyzing Hilbert functions and restating part of his work says that these pieces are non-empty if and only if. So, right, I did my decomposition over all polynomials. It's certainly true you can have rational polynomials which for large values don't give you integers, so they can't possibly be the Hilbert polynomial of anything. But even among the polynomials which take all integer values, some of them are not the Hilbert polynomial of anything. And Macaulay told us how to understand these things. He says, if there exists integer vector or tuple of integers, which will be all non-negative, in fact, even positive, that satisfy two conditions, at least the way I'm going to phrase it. First is this sequence of integers is non-increasing. So I think the combinatorialists would usually call such a thing an integer partition. And I will certainly use that language and think of this as an integer partition. And wow, what does it have to do with the Hilbert polynomial? It tells us we can write the Hilbert polynomial as a sum of very special polynomials, namely those that can be expressed as binomial coefficients. In this slightly strange way. So I think of my binomial coefficients as a polynomial in T. So if you think of many different ways to think about binomial coefficients, but if you just expand it in terms of factorials, I'll get a product of things involving t's in the numerator and a product of things involving the integers in the denominator. And that gives me a rational polynomial in T. In fact, each binomial coefficient is of degree given by the denominator in this expression. So if you can write a polynomial as a sum this way, then it is the Hilbert polynomial of something. And if you can't write it this way, it's not the Hilbert polynomial of anything. And so those pieces are empty. This actually, I mean, looks a little complicated, but you can just use the greedy algorithm to produce this. So maybe I'll back up and just have one example. If we take the Hilbert polynomial for a twisted cubic, I see that it has degree 1. There's a linear term. So I do the greediest thing I can. And I take my biggest lambda to be 1. And I get, well, in this case, just t plus 1. So when I subtract it, there's still a linear term. So I repeat, I need another linear guy. I get a t, and that gives me, when I add them, 2t plus 1. So there's still a linear term. And so I do this. This gives me 3t. So there's no linear term left. And so I do the next term, which is a 0-degree term, and that gives me the Hilbert polynomial in this expression. So the greedy algorithm always gives you this decomposition. So this expression that Macaulay came up with is really an effective way to tell whether a rational polynomial is a Hilbert polynomial of something. So it's quite nice. I should say, not only did he not talk about Hilbert schemes, because they weren't available, he didn't quite phrase it this simply. He didn't have the integer partition. He certainly had binomial coefficients, but I would say if you were going to phrase it in terms of interpartitions, Macaulay's original expression really involved the conjugate partition. So it's slightly different, but using well-known identities on binomial coefficients, you get this. So not so complicated. So we know when these pieces are non-empty, and we see it sort of has a nice way of determining that combinatorially. We know even more. Hartshorne, in his thesis, and only shortly after Grothendieck proved the existence of things, shows that every non-empty Hilbert scheme of the form we're interested in is path connected. So in fact, he proves it even better. He constructs a chain of rational curves on the Hilbert scheme connecting, well, any 2 points. He goes through a central point. He shows there's a special point that he can take an arbitrary point and choose a chain of rational curves and get to that point, so he gets the connectedness in a particularly nice and strong way. I should say it's not the usual definition for sort of rationally chain connected assumes you're working on an irreducible variety, and you get much stronger things. This, in general, is not irreducible, so I don't think I should use that language. In Alison Reeves' thesis, and appearing in a joint paper with her supervisor Mike Stillman, sometime later, 97 in fact, they analyzed that special point that was the center of Hartshorne's analysis, and they showed that every non-empty Hilbert scheme has a smooth point. So there's some point on a Hilbert scheme whose such that the dimension of the space at that point is equal to the dimension of its tangent space. And so I think, well, you'll see in a moment why at the time that was sort of surprising. So it suggests that things aren't so bad. And the goal of this talk is sort of to extend that and to classify all smooth Hilbert schemes of the form we've been discussing. So I should say all three of these results that appear on this page, unlike Grothendieck's original results, really do apply only to projective space. I don't know an analog of Macaulay's result for any other projective variety. There's no analog known for Hartshorne's result for other projective varieties. And Reeves and Stillman's result, again, we don't have an analog for any other projective varieties. So, I mean, not even schemes, even smooth, nice projective varieties, I don't know how to extend any of these three of results, which is both interesting and a little sad in some sense. So maybe I'll put a box around this to emphasize that that's the central player. Got too much there. Okay, so this is the good news. We do know some nice things about these components, and maybe we can get at the smooth guys. That would be wonderful. There are several other things known that make that seem maybe overly optimistic. Let me talk for a moment about the bad news. So the first bit of bad news, appearing only in publication only a year after Grothendieck's construction, was due to Mumford. And this appears in one of his pathology papers. He shows that an irreducible component of a particular Hilbert scheme is badly behaved. So he was interested in nice objects, so elliptic curves in projective 3 space, and turns out the Hilbert polynomial in question was 14t minus 23. From my point of view, the actual polynomial isn't so interesting. The fact that it's in 3 space is, I think, somewhat interesting. And so these are nice curves that are very pleasant to understand. And he shows that he shows one. I should be more careful. Only one component. Irreducible component is generically non-reduced. So from the point of view of singularities, singular at every point. So the fact that there is a smooth point, right? There can be whole components where things are pretty horrible. There's no chance of finding even one smooth point. Building on this theme, Ilya Hershkovitz and Mazzini. In fact, a fair bit later, but before the smooth results due to Reeves and Stillman, shows that the number of components, irreducible components, again, they concentrate on the interesting case of space curves, and they consider lots of them. So they're going to write the Hilbert polynomial, emphasizing that the leading coefficient is the degree, and writing the constant term in a way that you can see the arithmetic genus. They do this for space curves. And they show that the number of components is not bounded by a polynomial in the coefficients, as I said, the degree and arithmetic genus of the curve in question. So there can be a single component can be horrible, and the number of components can be uncontrollable. And then finally, maybe put the nail in this coffin, Ravi Vakil, in a celebrated paper called Murphy's Law. Murphy's Law in English is usually paraphrased as everything that can go wrong will go wrong. And what he translates this mathematically as every singularity type So by singularity in this context, I mean singularities that can be defined by polynomials with integer coefficients, and we put a very mild equivalence relation on them. Essentially, you can do products with intervals or make cones over them, cylinders over them. Every possible singularity type appears in some Hilbert scheme. And in fact, Ravi proves that this holds for many moduli spaces, not just the Hilbert scheme, but in particular, it's enough to consider Hilbert schemes in P4. He doesn't even need the ambient space to be very large to show that every singularity type appears. So this is, in some sense, the bad news. If the earlier slide was good news, this tells you that our hope of understanding all Hilbert schemes is wildly optimistic. We're not going to classify all Hilbert schemes in any strong sense. The components themselves can be bad. The number of components is horrible. And no matter how bad you think the singularity is, you can find one that's worse somewhere on a Hilbert scheme. Well, Mumford's is pretty explicit. The other ones are a little more existential. There's procedures for producing lots of points, but given a particular polynomial, they don't tell you whether you should expect lots of bad singularities or lots of components. So I think it leaves some elbow room for some reasonable Hilbert schemes to be in the mix, but how to identify them? Well, if we could classify smooth ones, maybe those would be the nicest possible ones. But it does beg the question, are there any smooth ones? Maybe this was a really easy question. There are no smooth ones, and we're done. Fortunately, that's not the case. So there are some well-known smooth examples. And let me give you a little flavor of them because they are suggested. Maybe three types of well-known smooth ones. First, we'll observe that the subscheme X in Pn is a linear subspace, let me call it of dimension lambda1 minus 1, linear subspace. Right, maybe the easiest type of subspaces, if and only if, well, you can tell from its Hilbert polynomial. Its Hilbert polynomial must be given by a single binomial coefficient where we know what the denominator is, because that gives us the dimension of things in question. So this is actually a very easy analysis of Hilbert polynomials to see this. And so what it means in practice is that when our integer partition has precisely one part, the Hilbert scheme is easy to understand. The Hilbert scheme in projective space is just a Grassmannian. In fact, we know what the dimension of the pieces are in the projective notation. So Grassmannians are among our favorite. They're certainly smooth and very pleasant varieties. So there are some smooth Hilbert schemes. All the Grassmannians are there. And certainly this observation was well known, in fact, was part of the motivation, I think, for Grothendieck at the beginning. He wanted to extend Grassmannians to a larger, to deal with nonlinear sub things. And so one way to think of the Hilbert scheme is a generalization of the Grassmannian. But that gives us an interesting class of smooth guys. It's sort of, in some sense, the opposite end of the spectrum. We can take a closed subscheme and recognize that it is a hypersurface. Of degree little r, if and only if again, we can recognize it from its Hilbert polynomial. In this case, well, I think the first thing I would have thought to do was a hypersurface is given by a single equation. And so if you consider the polynomial ring, mod that equation and take the minimal free resolution, well, you get a copy of the polynomial ring and a shift, which, there's only two terms in that complex and you know them all quickly. And so you can compute the Hilbert function, in fact, but certainly the Hilbert polynomial from that description. And if you do a little bit of rearranging using binomial identities, one way to write down what you get is as this sum of binomial coefficients. And this is the expression that, at least the way I described Macaulay's result, tells us. So again, from the Hilbert polynomial itself, we can recognize whether something is a hypersurface. And so this tells us that if we have very special partitions where all the parts are equal to n, and I'll use this notation that's common for integer partitions to write as an exponent, not to mean I'm multiplying n by itself r times, but it's saying I have n copies of that. So r is the multiplicity of the part. Then we also understand this, right? Because if the hypersurface is given by a single equation up to a scalar, I just need to know what the coefficients are. And I know how many monomials there are in this situation. So our Hilbert scheme just becomes a projective space. And you have to count the number of monomials of degree r in the polynomial ring in n+1 variables, and you get this expression. So we have another nice example of smooth Hilbert schemes. Again, these two were well known even before Grothendieck introduced them, although they weren't called the Hilbert schemes. This idea is long-standing. The third one is, well-known varieties, but the connection to Hilbert schemes seems to be less well-known. So for all lambda, such that we have distinct parts, so partitions where lambda 1 is strictly bigger than lambda 2, strictly bigger than lambda r, strictly bigger than 1, then we can also describe the Hilbert scheme. And it's simply a partial flag variety. You make a flag of linear spaces. In fact, the dimensions of the linear spaces are, in analogy with the Grassmannian case, lambda 1 minus 1, lambda 2 minus 1, down to lambda r minus 1. You can write down what the Hilbert polynomial is for such a partial flag variety, and you get the decomposition we've been describing. And the amusing part is there's nothing else in this guy. And in fact, the maybe thing that makes it slightly interesting is the lambda r strictly bigger than 1 is necessary. If lambda r is equal to 1, then points corresponding to partial flags are in your Hilbert scheme, but there are other things in your Hilbert scheme. Typically, there's other components. So not all partial flag varieties are Hilbert schemes in their entirety, but in some sense, most are, or many are. So there are nice examples of smooth Hilbert schemes, and this maybe makes it possible, or if you're really optimistic, you could try and understand all the smooth ones. So let me talk a little bit about our result. So the main theorem, this is joint work with Roy Skjelnes, who's at KTH, and myself, to appear on the archive any day now. It says that the Hilbert schemes we're studying is smooth if and only if one of the following conditions holds. So there's a couple cases, well, 6 cases, in fact, the way I'm going to describe it. The first case, which I'll label 0, is a case that is well known to experts already. If the ambient space is small, if we're on the projective line or the projective plane, then we get smooth things. In fact, Fogarty, famously proved that, in fact, you don't even need projective space. If you have points on a projective surface, then the Hilbert scheme is smooth. And in fact, his results cover this case completely. So that's not new, but nice, and has to be on our list. The remaining conditions don't say anything about the ambient space. They concentrate on the integer partition. So I think, at least from my perspective, the most interesting case is if the smallest part in your partition is not equal to 1, it's bigger than 1, then you get smoothness. So for my, at least if you sample Hilbert schemes using this integer partition, this says there are lots of smooth examples, which I like. In particular, this includes all the partial flag situations that I talked about before. The third situation, well, I have to add the uninteresting partition of 1. And then we have a slightly more interesting partition, which has potentially 3 distinct parts. N can appear with multiplicity r minus 2. Then I have a part which is really unspecified, and the smallest part has to be equal to 1. And I need the little conditions on the parameters. First of all, I want the multiplicity of the biggest part to be non-negative, so that's not a real or not an interesting condition. And the potentially third part can be anything between n and 1. So all possibilities are allowed for that middle one. So unlike the first two, these are quite specific partitions, right? This one can either have 2 or 3 distinct parts, and the largest part has to be n, and the smallest part has to be 1. The remaining ones are variations on that theme. So we could do the largest part is n, and this time I'm allowed to, well, have a second parameter s. The intermediate part has multiplicity s plus 2, and the last part is equal to 1. So quite specific partition. Again, there's 2 conditions. I need the multiplicity of n to be positive, and I need to say something about the intermediate guy, and unlike the previous case, here the intermediate guy is strictly between. Can't be equal to n and can't get all the way down to 1. In fact, it can only go down to 3. So strictly between things in question. So the fact that this part can't be 2 is a little weird, and well, that's the next case deals with that. So case 3 and 4 are really quite similar. They just have slightly different parameters. Instead of subtracting, well, I have to subtract more. This intermediate partition has to have higher multiplicity when it's equal to 2. Or the minimum multiplicity has to be higher. It's a better way to say that. So again, the condition is that the multiplicity of n has to be positive, and that's, well, I've specified that the intermediate part is 2, so there's no other condition there. So conditions 3 and 4 are quite similar, except for the minimum multiplicity on the middle guy. And finally, the last case, maybe the least interesting one, says you can have, well, your largest part has to be n, and your smallest part has to be 1 appearing 3 times. And again, I have a minor condition. So we have 6 cases. The first 2 are probably the most interesting. The other 4 are relatively specific Hilbert schemes. These guys, in fact, all 6 situations have appeared in the literature before. So as I've already mentioned, Fogarty in 68 dealt with the first case, and in fact, his techniques also deal with the last case. He deals with parts of size n correspond to components that are hypersurfaces, and Fogarty tells us how to understand those completely. And so the 5th case is really 3 points on a projective space, and that was known to be smooth. Cases 1 and 2 were analyzed by Andrew Stahl. His work just appeared in print this year, amusingly part of his thesis, so a 3rd thesis related to Hilbert schemes. And he showed by analyzing Borel fixed points that these guys were smooth. And much more recently, in fact, only appearing as a preprint at the end of last year, Ram Kumar, appearing as a preprint, he was actually motivated by Andrew Stahl's work, and so analyzed what happens when there's 2 Borel fixed points on these Hilbert schemes. And as special cases, he found that these classes were smooth. So we in fact, in the literature already, all of these classes appeared, and so they were known to be smooth. The miracle or the surprise is that these are all of the possibilities. There are no other ones, which I was surprised at. Let me give you, since we have the technology, a little photo of Roy so we can remember what he looks like. So what else do I want to say about this? So the first case, as I said, that's well understood. The second case, I think, is probably the most interesting and includes all the partial flags. In what I called case 2, we see when the partition has a unique part of size 1, that's really the Hilbert scheme of a point. And the Hilbert scheme of a single point gives you back the underlying thing, so we get projective space back, and so that's very nice. We knew that should be smooth. Lambda r minus 1 in this case could be equal to 1, and if r was equal to 2 and it had 2 parts of size 1, that would be the Hilbert scheme of 2 points. And again, that was already known to be smooth for all projective spaces, not even just surfaces. And the last case, as I mentioned, when r is equal to, oh, should that be 3? That's a typo. Let me fix that. That's supposed to be a 3. So those ones are quite nice. The conditions 3 and 4 are really similar, except for the minimum multiplicity on the intermediate guy. And so what explains the gap between these guys? Well, in fact, 2 well-known Hilbert schemes explain the gap between the 2 and the 4. The first being the Hilbert scheme that parameter has a point corresponding to 2 skew lines, just 2 skew lines. That would correspond to the partition 2 squared, comma 1, right? 2, 2, 1. And that has been analyzed, and it has 2 components. The component that corresponds to the smooth thing that Reeves and Stillman had, that component doesn't have the 2 skew lines. And so that explains part of the gap. When you have three copies of 2 and 1 copy of 1, the Hilbert polynomial you're getting there is the one we saw before. That's the twisted cubic. And I think Ragney was even on the list there. Ragney analyzed very carefully the geometry of the Hilbert scheme of twisted cubics. And again, there are 2 components. Each one is smooth, but the one that includes the smooth point identified by Reeves and Stillman is not the component that contains the twisted cubics. And so these 2 well-known examples, which are singular because they have multiple components that intersect in interesting ways, explain the gap between 3 and 4. So we sort of understand these things. And I think it's amusing that, well, this case produces lots of examples and all the other ones are pretty special. How do we end up proving such a result? How did we even discover such a result? So we didn't set out to do this directly. We were interested in fact, it started when I was visiting Roy at KTH. We were interested in Andrew Stahl's work, in particular this first case, and trying to understand the geometry of those Hilbert schemes, the points on them, what we could say about them, right? It's a smooth variety. We should be able to say lots of good things about those. And so we recognized some structure, which I'll tell you about in a moment. And then we started to do some computations in Macaulay 2. And the miracle was when we sampled Hilbert schemes using these partitions, when there was a small number of 1s, we were actually able to do all sorts of calculations. And so, in fact, the original discovery of this was a Macaulay 2 calculation where for n equals 3, 4, 5, 6, and 7, I analyzed thousands, in fact, awfully close, just under 10,000 different Hilbert polynomials, computed all the Borel fixed points, and computed the dimensions of the tangent spaces at all those Borel fixed points. And that allowed us to identify these as smooth ones. And so there was something I had played, in fact, with Mike Stillman for many years, trying to analyze various Hilbert schemes. And if you sample the Hilbert polynomials in other ways, you quickly find examples you can't compute. And so something about organizing our thoughts with these integer partitions led to examples that were computable and understandable. I don't fully understand that, but it certainly seems to be true. So let me tell you a little bit more about the geometry. Not only, I mean, we don't get this result by some simple analysis. We have to say more about the geometry of these guys. And we need a little vocabulary to understand the geometry. Somebody joined. Okay. So first, some definitions. The first one is actually quite classic. I don't even know who first defined it. It's been around in algebraic geometry for such a long time. So we'll say an intersection or an inclusion of two projective varieties. So y sitting inside x is residual if there exists two things. First, linear subspace which I'll call capital lambda. It is going to be related to our lowercase lambdas. And a hypersurface which I'll call D, thinking of it as a effective divisor in our linear subspace, such that two things hold. The first is, well, crucial, but not the real interesting part. These two things sandwich the larger one of our substring. So the divisor is contained in X and is contained in the linear subspace. So I need that. But the more interesting part is the ideal sheaf of X is the ideal sheaf of Y times the ideal sheaf of the hypersurface. So this is a scheme theoretic version of saying that X is the union of this other projective variety and the divisor, the hypersurface. So X decomposes in this nice way. And I think this language first arose in trying to understand excess intersections and residual intersection formulas. So the definition I've given here is almost verbatim from what you can find in Fulton's intersection theory. So this is the basic idea, and what I want to do is have a flag version of this, which seems to be somewhat novel. So a residual flag is simply a chain. So we'll start with the empty set and contain x sub L, x sub L minus 1, and we work our way up to the first guy, the one we're most interested in, of such inclusions. So first of all, what does it mean that the empty set contained in XL is a residual intersection? It means that XL has to be a hypersurface in some linear subspace. So each of the XLs is a hypersurface in some lambda, and the dimensions actually, I use capital lambda because the dimension of those linear spaces are going to be given by what were lowercase lambdas before. So we understand the bottom one's a divisor, and then the next one up is the union of a divisor and some hypersurface and the guy below and a new hypersurface, and we keep working our way up to get to the one that's most interesting, the top guy. Okay, so this is Okay, not so clear why it's useful, but a definition. And the theorem explains why I've made the definition. It says points in a smooth Hilbert scheme of the flavor we're analyzing. Well, not for all 6 cases, only 5 of them. So I have to ignore the first case analyzed by Fogarty, satisfying conditions 1 through 5. Correspond to, well, there's 2 possibilities, either residual flag, which explains, at least initially, why we made the definition and how we came up with it, or it should be the union of residual flag and a point. So these, for the smooth ones, at least, well, in fact, for n greater than or equal to 3, we understand what the points correspond to. So we get some understanding of the geometry. We understand the schemes being parameterized by these guys. Amusingly, except when there's one integer part, except for the Grassmannian case, the things being parameterized are not irreducible. And in the first case, when we get residual flag, which includes the case 1 completely, so every time you're in condition 1, you correspond to a residual flag, this description actually allows you to give an alternative interpretation for the Hilbert scheme. It turns out to be a projective bundle over a partial flag variety. So in the first case, when it's a residual flag, every point corresponds to a residual flag, then you get a description of the Hilbert scheme as a projective bundle over a partial flag variety. And that's amusing and interesting. That in particular means you get presentations for its chowering, or just using standard techniques from Fulton's intersection theory. You also learn that its chowering is equal to its integral cohomology ring. Again, just using well-known techniques. So we really understand those ones very well. The case where it's a residual flag and a point, well, the first thing to point out, and it's sort of amusing, is all the other cases, well, case 5 maybe not so obvious that way, but all the other cases had a unique integer part equal to 1. And that's where the point comes in. The point is corresponding to that part equal to 1. And the 5th case, you had 3 of them, but 2 of the ones can be included in the residual flag. I can make a residual flag. If I have a linear subspace, I can choose a polynomial and get 2 roots to be those. So it takes a little bit to show that. In this case, we don't get a isomorphism between the classification of residual flags and a point. We only get a birational map. So if you take the parameter space for residual flags and you take the product with projective space, classifying a point, if the point doesn't lie on the residual flag, over that locis, it's isomorphic to the Hilbert scheme. But when the point collides or moves into the residual flag, you don't get an isomorphism. They can, you get some blow up. So the Hilbert scheme is only isomorphic to the product of the parameter space of only birational to the parameter space of residual flags cross projective space. There's a little bit of a blow up there. It's clear what, just from that description, what the support or what the center of the blow up has to be. We haven't worked out in detail what the scheme structure is on that, so I don't know if it's anything more complicated than the reduced guy. I don't know. But from this, we get a very detailed understanding of the geometry of the smooth ones. I would say in some sense, more numerous than you might have initially guessed, more numerous than I would have initially guessed, but also quite understandable. They're really just, in some reasonable sense, generalized partial flag varieties. Maybe this is a good place to stop.